Okay, guys, in this video lesson, we're going to take a look at electric forces now. So we're going to start putting some math to our concepts, all right? So first of all, when you have charge, there is attractions there, or there's repulsion. So if you have an attraction which causes movement, okay, or you have a repulsion that causes movement, there has to be a force involved, okay? We can't get movement without creating some sort of force. We can't get work done without creating some sort of force, right? All right, so that being established, let's take a look here. We're still going to talk about force. It's still going to be newtons, okay? We're going to focus on that force between two charged objects now, okay? It's a lot like gravity, okay? Gravity, there's always two different objects that would always have some sort of attractive force between them. That force always related back to the mass of that substance, or how much mass was there, and the distance that they were apart from each other, okay? Now, unlike gravity, electric force can be attracting, like gravity is always attracting, or it can be repelling, okay? So kind of keep that in mind that we have a negative force, that means we're attracting things together. If we get a positive force, that means we actually are repelling or repulsing that object, okay? Now, that brings us back to some of the basic ideas that we know about charge and forces. So if we have substances with the similar charges, okay, so they're both positively charged or both negatively charged, they're going to repel each other. If you have a substances, I should say, that have dissimilar charges, okay, or opposite charges, we could say. So one is positive, one is negative, they're going to attract each other, okay? That's where we get the idea of opposites attract, is from this idea, okay? Now, when it comes to strength of these forces, the overall effect for electromagnetism or electrostatic force we're looking at in this scenario is stronger than gravitational force. So we can actually use electrostatics to outdo gravity, okay? In reality, gravity is a pretty weak force. If you think about it, we need our entire planet to hold us down and drive us, to have us fall downwards. We can use simple little magnets to hold things up. We use a Van de Graaff generator, and with just a flick of the thing, within seconds, we had pie plates flying through the air, launching away from gravity. So we overcame gravity very quickly, very easily, with a very small device. With those repulsive force we felt with the Van de Graaff generator. Okay, so gravity weak, electrostatic force here much stronger. All right, now let's go back and review a little bit about protons and electrons, kind of how that works. All right, so protons we know is held together with neutrons in the nucleus. Okay, that interaction is being dealt with by something called the strong force. It is not something that we are going to deal with in here. Okay. It's allowed to happen because the strong force is actually stronger than the electrical repulsion that the two protons would feel towards each other. All right. So you might be wondering, if positive charges repel, why can more than one proton sit in a nucleus? Well, they do repel. The electrical force here is trying to get them apart, but there's another fundamental force that's stronger that's holding them together. All right. Now, the electrons, they are attracted to the nucleus by this electric force. Okay. This electric force, or this electrostatic attraction, is what creates that orbiting effect on our nucleus. So electrons would normally just fly away, except for they are attracted to that positive core of our nucleus. Okay. However, the farther the electrons get away from that core, the weaker that attraction is. So our outermost electrons are the ones that are most susceptible to being taken away. Okay. In the world of chemistry, that's how we get chemical bonding or ionic bonding. It's because we strip off those outside electrons. In the world of physics, it's really no different. We want to get a charged particle through either friction or conduction or induction or any of those things. We do it by taking the electrons on the outermost energy levels, or the outermost ones, because they're the ones that have the least amount of electric force holding them in. Okay, what that brings us to now is working with this idea of force and being able to relate the electron back to how much force is there. Okay, to do that, we need a new unit of measurement to work with. Okay, we know an electron has a charge of negative e's. Okay, so when we deal with protons, we actually can say that a proton has a charge of a positive e. So really, a proton is just the positive version of the electron's charge. Okay. Using that designation, we now are able to basically always talk about electrons and not worry about the protons. Now, the Coulomb is the SI unit that we use for charge. We haven't learned a lot about amps yet, or that kind of stuff yet, but the Coulomb is actually defined as 1 amp of current flowing per second of time, okay? And we'll get into amps more later, but you might be wondering, why is it such a weird number of electrons? Why is it not just something nice and even? The reason why is the Coulomb is actually defined by current flow and not number of electrons. Okay? But as a result of that, that Coulomb of charge that we get happens to equal 6.24 times 10 to the 18th electrons. So every time we can get 1 Coulomb of charge, this is the number of electrons that have to pass through that circuit or that position or that kind of space. All right. Notice the negative sign here because electrons have a negative charge, so we have negative coulombs here. All right. Now, if you do the inverse function of 6.24 times 10 to the 18th, you get a negative 1.6 times 10 to the negative 19th coulombs. Okay, this is probably the more useful way, or the way that we typically use this, but either one is usable. Okay, what this tells us is every 1 electron has this amount of Coulomb of charge in it. Okay, let's do a quick little practice problem. Make sure we have this down. In 5 minutes, a normal iPhone charger can deliver a max of negative 300 coulombs of charge to a phone. Okay, this is actually true. Okay, that's how the iPhone charger works. In that time, how many electrons are transferred? All right, so you know the amount of coulombs of charge. You know the relationship. You either can use this one or this one. So set up a simple dimensional analysis problem and solve it, and then pause the video and then unpause it when you're ready, and I will show you the answer. Okay, so here we go. We have our negative 300 coulombs of charge. If we use the first example, we say for every negative 1 Coulomb, we get this many electrons. So negative 300 times this divided by negative 1, and we get 1.87 times 10 to the 21st electrons. If you wanted to use this conversion factor, exact same thing, we have our coulombs of charge. It's a negative 1.60 times 10 to the negative 19th coulombs equals 1 electron, and we get the exact same number. Okay, so either of these conversions will work in either case. Okay, as long as you go back to these 3 layers of precision that we're looking at with these. All right, this becomes useful for us because if we know the amount of charge available, we actually can track the number of electrons that are flowing, which then is going to pertain to more useful information when we get into circuitry. All right, now, once we know that what a Coulomb is and we know how much charge is there, we need to be able to solve for the amount of force available. Okay, and by doing that, we go to what's called Coulomb's Law. All right, Coulomb's Law tells us that the force that we have available is equal to a universal constant for force times the charge of one particle times the charge of the other particle divided by the radius squared. Okay, so essentially what we're saying here is you take the charge of the 2 particles, multiply them, divide by how far away they are squared, take that times a constant, a universal constant, and that will tell you the force we have. Okay, Coulomb's constant is 8.99 times 10 to the 9th newtons times meters squared per Coulomb squared. Okay, the meter squared per Coulomb squared is needed here because we have coulombs times coulombs and meters squared here, so that helps cancel that out. Right? We know what Q is. That's our charge of each particle in our coulombs. Okay, so Q here stands for charge for particles. R is our distance, and N is the same force we've always used. All right. Now, looking at this, okay, hopefully when you see this equation, it jogs a little bit of stuff in your memory and say, wait a minute, force is equal to K Q1 Q2 over R squared. That looks awful familiar. Okay, it really should look very familiar to us because this is a replication of another equation that we use that deal with the universal force. All right, so this is the force of electric force. We had another very universal force that used a very similar equation, and that was gravity. Okay, so if you take a look, Newton said that the force of gravity is a constant, mass of one object, mass of the other object divided by the distance squared. Okay. In Coulomb's work, he realized that the exact same relationship works for charge compared to distance here. Not mass, but charge now. Okay, so it's not a coincidence. It's not just by happenstance. It actually makes sense in the world of universal forces that the universal force for electricity should be the charge of those things divided by that squared, or it's an inverse square of distance again. All right, let's do a little bit of mathematical practice now with this thing. All right, so we have the distance between the main sphere and the secondary sphere on a Van de Graaff generator is 15 centimeters. Right, so think back to the Van de Graaff generator example that we used. Main sphere is a buildup of negative 1.23 times 10 to the negative 15th coulombs of charge. And the secondary sphere still has a residue of charge on it that's negative 2.45 times 10 to the negative 7th coulombs of charge. Okay, so they both contain charge. What's the force between them? And then is this force going to be attractive or repulsive? All right. So before we can even answer the actual numerical value here, looking at our numbers and what's going on here, you should be able to tell me if it's attractive or repulsive. Okay. So pause the video, make a decision on this, solve the math, start the video again, and I'll give you the answer. All right, so hopefully you're assuming this is going to end up being a repulsive force because we have a negative charge and a negative charge. So negative and negative means that we have the same charge, so they should be repelling each other. Okay, we know our equation. We know the universal constant for electric force is 8.99 times 10 to the 9th newtons times meters squared per coulomb. We put in the charge of the main sphere, the charge of the secondary sphere, and notice how we divided by 0.15, not 15, because we need to be in meters to match the units. Okay, so you got to be in meters here. So if you didn't do that, you're not going to get 1.20. 0.15 squared. Put these numbers in, and we should get 1.2 newtons. And it is a positive force, which would also tell us that it is repulsive. Okay. Let's look at this idea through some qualitative value instead. All right. So if we were to double one of the charges in a scenario, so let's say we have 2 electrons or 2 particles or 2 bricks or 2 light bulbs, well, it doesn't really matter what they are, 2 objects, and one of them we're able to double its charge. How would that affect the force acting in that scenario? Okay. Think about it. Look for an answer. And here we go. Well, if we double the charge, we should double the force there. Okay. Now, let's change the sign of one of the charges. So let's say we make one of them positive, and then we turn it and make it negative instead. Okay. So if we flip the sign of only one of them, how would that affect the force that we have? Think about it. And here we go. Okay. Well, the force should change direction. Right? So if we actually were to change the sign from positive to negative, we actually can make the force go a different way. Okay? That becomes useful when we start talking about AC current. Change the sign of both charges. So if we change both of them at the same time, what would happen? Think about it. Right? Nothing should change. Right? If they both change signs, so that they were repelling before, then now we'll still be repelling afterwards. You just have opposite signs again. Okay? If they were attracting, they'll still attract because you're changing both of them. What about if we double the distance between the charges, though? Think about it. All right, here we go. Okay. Well, because it's a squared feature, excuse me, we double the distance, it's 2 squared, so it's 4 times weaker. Okay. It's 4 times weaker. If we tripled the distance, it'd be 3 squared, it would be 9 times weaker. Okay, so exactly just like gravity, if we got twice as far away, the gravitational pull was 4 times less. If we got 3 times farther away, the gravitational pull was 3 times less. What if we double both charges? Think about it. Here we go. So the force now would be 4 times stronger. Because if we double the charge in each one, okay, and you're multiplying them by each other, it's 2 times 2, okay, because you double them both, we end up getting 4 times more. All right. If you tripled one and you doubled the other, you would get 6 times more. If you tripled them both, you'd get 9 times more. Okay, between those two things. Be ready to be able to qualitatively look at that equation and answer questions like this also. Okay, not just using the equation blindly and plugging numbers in. All right. All right, guys, we're going to end the video there. And the next one, we're going to talk about electric fields. Thank you.